Well, hello, everyone. Hello to our local, in quotes, people at the Wolfram Technology Conference and to outside people watching this on our live stream. So we've got two things to do tonight. Well, it's tonight for me. One is something that I always find very interesting, which is our Wolfram Innovator Awards. And the other will be for people who are at the technology conference, will be a Q&A based on my keynote of a couple of days ago. Okay, so the first and big thing is our Wolfram Technology Awards. And we established this program about 10 years ago now to recognize particularly interesting and innovative uses of our technology that came to our attention. And there are no doubt many more, many very interesting things going on, but we don't always hear about them. We want to recognize those that we do hear about. And each year from around our company, we have selected a limited number of awardees. Actually, this year, because everything is virtual, we have been able to expand the number a bit. And I'm happy to say we'll be awarding 19 Innovator Awards this year. So let me just remind people, last year we had a fascinating group. These are our Innovator Award winners from 2020, also virtual. This year, I will say we have 19 awards. And I'm going to, in each case, I'm going to try and say something about the people or organizations behind the award and a little bit about what they do. I should apologize in advance to anybody where I get the facts wrong. I'll try not to. I would like to point out that many of our award winners have given talks at the technology conference this year, and you should be able to find the talks that have already been given that you can replay through the conference system. I think there's maybe one or two more still to come, so watch out for those. So I want to say that this means that some of the people who we are giving awards to are people who I have known for many years. The record holder this year, I believe I have known for 42 years. But others I've had the pleasure of meeting only today. So there will be some differences in what I'm able to, in the stories I'm able to tell about different people. But I hope to give you some flavor of some of the things that our award winners have done and something about those individuals. All right. Well, without further ado, let me go into our collection of award winners. So our first Innovator Award, and we're going to just do them by alphabetical order of last name here, first individuals and then organizations. So our first award of the evening goes to Giresh Arabile of Saigram Technologies Foundation and a couple of other companies. So Giresh first used our technology as part of his doctoral work on carbon nanotubes. Out of that work came his first company, Mulk Bits, Sensors and Data, which he founded in 2015. Its goal was to use Raman spectroscopy to create a handheld scanner for soil properties to be used in agriculture. And he also built, just this last year, demoed at the Consumer Electronics Show, a breath AI prototype for detecting things like blood glucose levels, presumably, its name suggests, through breath output. But the thing that's been most notable to us is Giresh's work with his Saigram Technologies Foundation. Its goal is to bring computational thinking to a wide range of underserved communities. Particularly, he's been working with kids in the tribal areas around Pune, India, which is where he's based, and delivering computational thinking to them using Wolfram language and Raspberry Pi. And he was telling me about the fact that they're able to work on all these different areas and show kids things about words and anatomy and so on. He says, even though the kids don't always know English that well, they're still able to interact just fine with Wolfram language, including kids down to age 8. And that's something where the use of Raspberry Pis has been particularly valuable because not all of these schools have ready access to internet connectivity, and Raspberry Pi is something that can be used even in that situation. And I was telling Giresh, I'm hoping that some of his students will one day be able to come to our summer camp for high school students, and look forward to that. So our first award goes to Giresh Arabile. All right, well, let's go on then. Okay, our second award of the evening goes to somebody I have known for quite a long time, Bruno Buckburger, physicist from CERN, now retired. And Bruno, well, started his career having studied theoretical physics in Paris, and started off researching amplification of acoustic microwaves in cadmium sulfide, trying to use, instead of having traveling wave tubes, use crystals to transmit microwaves. But in 1967, he discovered CERN, the European Center for Nuclear Research, the particle physics center of Europe, and started working on the development of accelerators there. And the first accelerator he worked on was the ISR, which I remember from back when I was a kid doing particle physics. I think that stood for intersecting storage rings. But it was a proton, what was at the time considered a high energy proton collider. And Bruno started working on design of magnet systems for both accelerators that just accelerating particles, either typically in a ring, and then intersecting rings where particles could collide and where one could do experiments to watch the results of those collisions. So in the early days, when accelerators were being designed, there was a lot of numerical computation that was done. What Bruno realized was that some of the more complicated things that had to be worked out really needed symbolic and algebraic computation. So when the first antiproton source at CERN, Bruno worked on calculating the way that should be set up using Schoonship, which was an early algebraic manipulation program that had been developed actually sort of around CERN, starting in the 1960s. And then Bruno continued to work on antiprotons at CERN at Fermilab, and then took a sabbatical at Lawrence Berkeley Lab, where he worked on the advanced synchrotron light source. That happened to be right in 1989. And at that time, the first version of Mathematica was coming out bundled with the Next computer that Steve Jobs had developed at Next, the company between his stints at Apple and at Apple. I should say that Next and CERN actually had an interesting history, because the theory group at CERN bought a bunch of Next computers for the sake of running Mathematica. That was Steve Jobs' calculation that if you bundle something really useful like Mathematica on your computer, people will buy the whole computer just to get that software for free, so to speak. That worked well for the CERN theory group. The system administrator of that theory group was a certain Tim Berners-Lee, who ended up trying to figure out how to network those computers in a really good way, and invented the web there. But that's a different use of Next and CERN. What Bruno did was then to start using the symbolic computation capabilities of Mathematica, now Wolfram language, as well as numerical and graphical capabilities to work on lots of design processes at CERN. He also built two significant packages that have been distributed, one called Geometrica and one Beam Optics. Geometrica was kind of a pioneering system that did exact symbolic geometry. Now we have many of those capabilities in the synthetic geometry system that is now built into Wolfram language, but Bruno's Geometrica kind of pioneered a bunch of those ideas. His beam optics system was used for the LHC, the Large Hadron Collider, and also for studies of things like muon colliders. That's a kind of a particle device that I've been hoping since I was a kid would finally be built. Maybe it will be one of these days. Bruno is now retired from CERN and living in France. His big activity right now is writing a book about particle accelerators using Wolfram language. And he tells me he has now finished the 10th chapter of a 12-chapter book. So I'm looking forward to seeing that book, maybe a draft of it at least this year. So it's with great pleasure that we give our Innovator Award to Bruno Orton. All right, let's move on. Our next award of the evening goes to Trevor Bennett of Starfish Space. And Trevor started using Wolfram language as in his PhD, which was on the subject of detumbling spacecraft. After his PhD, Trevor Bennett worked at NASA Goddard and JPL on robotic missions, and then at Blue Origin on the New Glenn spacecraft, which is the orbital successor of the New Shepard spacecraft that got its day in the news yesterday. He's been for the last couple of years being a co-founder of Starfish Space. The goal of Starfish Space is to create kind of a new component to the space industry where they're building things which are able to actually have robotic missions that service spacecraft already in orbit. So for example, a space tug, I think there's an animal theme going here, I believe that's called the Otter, that is a space tug that can move a satellite from one orbit to another, and also potentially the ability to actually fix satellites, which weren't always designed to be fixed in orbit, to be able to make, to be able to swap out electronics and so on in orbit. And apparently they've already launched their first satellite at Starfish, and hoping to build a whole industry based on this. I might mention that one of Trevor's achievements during his PhD was using Wolfram language to generate linearized relative orbit elements, for which I'm going to guess what those are, because I know when you specify the orbit of a satellite, you usually use these things called two-line elements, which are kind of a few mathematical parameters that specify an orbit. And I'm suspecting that Trevor's invention here has to do with figuring out how you get from one orbit to another. And I suspect that's highly relevant if you're going to go and build space tugs and so on. So our next award then goes to Trevor Bennett and of Starfish Space. All right, next for the evening, our next award goes to Bruno Buckberger, somebody I've known for a long time, founder and professor emeritus of the Research Institute for Symbolic Computation, otherwise known as RISC, at the Johannes Kepler University in Linz, Austria. And Bruno has been a long-time pillar of the symbolic computation community. His first breakout work was his PhD thesis in 1965, in which he developed what he called Grosvenor bases. It's one of those cases where somebody who invents something specifically names it after somebody else. In this case, Bruno named it after his thesis advisor, Wolfgang Grosvenor. And Grosvenor bases are a key idea, an element of lots of polynomial computation algorithms. If you have a collection of polynomials, the Grosvenor basis is a kind of simplified collection of polynomials that have the same roots as the original polynomials. And that might seem like an obscure idea, but it's turned out that it's sort of a central idea in developing lots of kinds of algorithms. And in fact, that idea has a certain confluence, and I use that word as a bit of a pun, with a bunch of other ideas associated with term rewriting systems and other kinds of transformation processes. And in fact, that very idea shows up again in this phenomenon we call causal invariance that is central to our physics project. So Grosvenor bases, while they are the polynomial case, what Bruno realized back in 1965 was part of this kind of general story of the confluence property, or what we've now generalized a bit to call causal invariance, that turns out to be in our physics project sort of the thing that allows one to have consistent representations of space-time and quantum processes and so on. Well, Bruno's had a very distinguished career in academia and in industry. He created, back in the mid-1980s already, the world's first software park in the Linz area in Austria. There are now 3,000 people working there. It's spun out a large number of companies over the course of years. His RISC Linz Institute, I visited long ago, and it is a very lovely place in a castle, well, a small castle. That's been a center for research in algebraic computation. Another big project of Bruno's has been his Theorema system, built with a number of colleagues. Theorema is a Wolfram language Mathematica based system that has been developed for a long time, that is a formalized mathematics system, kind of in many ways a forerunner of some of the ideas of proof assistance, but in many ways richer than the proof assistants that have arisen in recent years. And Theorema is a fully notebook environment system that allows one to represent and generate proofs of mathematical theorems. And I think Theorema is about to get to a new version which will start to use some of the latest technology that we have, and I'm really looking forward to that. So our award goes to Bruno Buckberger. Oh, look at that. That's one of these confluence processes illustrated in that image. And I think that background there is a piece of Theorema output. All right. Well, our next award for the evening goes to Richard Carbone. Richard is a digital forensic analyst at the Defense Research and Development Organization in Canada. Richard told me that he started off as kind of an IT-ish person working on things like Unix. One of his early achievements after joining the Defense Department in Canada was broadening the kind of software that was used there to include open source software of various kinds. But he has been, in recent years, really using Wolfram language both extensively and I think in a whole variety of functions around digital forensics. And I think the picture there is one's presented with, here's a disk drive, here's a bunch of files, here's a bunch of network traffic that's happening, kind of try and analyze for various kinds of law enforcement or military purposes, what's going on here? Can one tell what's happening? And this is a kind of place that is really ideally suited to the sort of multi-paradigm approach that we've spent so much effort on in Wolfram language. And Richard has developed a whole collection of tools for different purposes for doing these kinds of things, whether it's text processing or image processing or binary file analysis. These are all things that Richard has worked on using Wolfram language, and these things have been deployed in the field in Canada for digital forensics. So our next award goes to Richard Carbone, and I'm guessing some of these pictures are part of Richard's toolkit for binary file analysis, and he's also been working on steganography and the question of how you can do things like telling steganography is hiding messages in images, but there's sort of a variant of that which has to do with figuring out, is this image a real image or is it an image that's been photoshopped and so on, and being able to detect those kinds of things using whatever techniques are possible, I think now including areas like machine learning and so on. Our next award goes to Bill Gosper. Bill is the local winner of the person I've known longest. I first met Bill at a Maxima users conference in 1979. And Bill had been at MIT in the 1960s and was part of a group that produced a thing called HackMem, which is a large collection of, in many cases, now very famous little computer and mathematical hacks. It's a kind of collection of aphorisms. I was just pointing out to Bill that it will be 50 years next year since HackMem was first officially published, and it's probably time for a version 2. And talking of a version 2, Bill is a tremendously prolific producer of mathematical results created using Mathematica. And I get mail from him with great regularity every few days with a new and often very surprising and unusual looking mathematical result. I like to imagine that if I'd been around in the 1910s and had been lucky enough to be in correspondence with Ramanujan, I would have seen similar kinds of things produced. But now we have Bill plus Mathematica producing a kind of Ramanujan-like stream of mathematical results. So Bill, I think his first claim to fame was probably when the Game of Life was first coming out around 1968 or so. One of the questions was, in the Game of Life cellular automaton, if you start with a finite sized configuration, could you ever get a configuration that would grow forever? And Bill found one, the glider gun, and that was kind of, I think, his first big claim to fame. And through that, got acquainted with Martin Gardner, longtime mathematics writer. And Bill connected with many other things with Martin Gardner over the years. Bill has invented a bunch of algorithms for symbolic computation, including ones for symbolic summation, which we use. And he's been a long-time enthusiast of continued fractions and has invented a whole bunch of algorithms for continued fractions, some of which we also use. For a while, Bill was the person who had the record for having computed the largest number of digits of pi using algorithms that he developed. He's also been a long-time studier of space-filling curves. The Gosper curve is a sort of dragon-shaped kind of curve that just goes in a line but fills space and has many very interesting properties. Bill has been based in the San Francisco Bay Area for a long time with various stints at various organizations. I remember visiting Bill, must have been in 1980 or so, at Xerox PARC, the Xerox Palo Alto Research Center, place where that was I think the very first place I'd ever seen a bitmapped display interface. And Bill was showing off the game of life running on a Xerox Alto, I think, computer, as well as showing me, look, there's this laser printer that prints in color and prints at very high resolution. And I think at the time, there really weren't even laser printers out in the rest of the world, but Xerox, being the company that it was at the time, had produced the first color laser printer, and Bill had made this remarkable pattern that I'm sure I still have in my archives somewhere with elliptic functions, I think, some elaborate color printout. Bill ended up working a bit with Donald Knuth at Stanford and contributed some things to Don Knuth's books. He also, when Mathematica first came out in 1988, we pulled Bill in to help us make demos, and Bill notably made, actually for a group at IBM that was distributing Mathematica on IBM RISC computers, made a trefoil knot, which at the time was high-tech 3D graphics, and produced a poster that's a trefoil knot, and it says Mathematica spoken here underneath. And those are now collector's item type posters, but that was Bill's contribution there. So in more recent times, Bill's just discovered a huge range of mathematical results. They tend to be quite aphorism oriented. And I'm sort of really hoping that somebody is going to volunteer to make the collected aphorisms or works of Bill Gosper, because there's so many of them and they will be so valuable in the future. Even if they have not been collected into very organized papers or anything like that. But in the last 15 years or so, Bill has had a new activity, which is dealing with the next generation. And somehow Bill manages to find these amazingly bright, very young kids, initially mostly in the Bay Area, now also elsewhere, who learn mathematics and Mathematica and Wolfram language with him and go on and produce remarkable and very surprising research results. I happened to visit Bill and some of these kids a few years ago and had the very interesting experience of walking into this room with a bunch of, I think, 11-year-old-ish kids, and they're talking to me, and they start talking in code, and they're speaking Wolfram language code. It's the only time I've ever seen or heard somebody speak Wolfram language code. I think they were very disappointed that I had to say to them, I'm not used to understanding this stuff in spoken form. You have to slow down. And it takes me a while to kind of visualize what you're saying. And actually that moment caused me to realize that we really do need to make a way to have spoken Wolfram language code, because it's something that will also be useful when for educational purposes and so on. But Bill has been educating this remarkable collection of well, initially they start with him at age 10 or so, but some of them are now grown up and doing lots of good things out in the world with math and so on. So anyway, our award here goes to the very unique Bill Gosper, and I think that must be one of the space filling curves that that I get regular mail about. Okay, well, our next award of the evening goes to Ming Shu. Ming got his PhD at Caltech in economics and is now at UC Berkeley in across the business school and the neuroscience institute. And those affiliations already perhaps give some indication of what he does. He's in the new and emerging and very hot field of neuroeconomics, concerned with the question of how do we understand from neuroscience how it is that we make economic decisions and so on. He has been using Wolfram language for lots of purposes. Initially, I think in his PhD thesis, for studying evolution of prices in double auction markets, according to traditional general equilibrium theory in economics. I think he's kind of been getting down the stack of behavioral economics, down into consumer neuroscience, neuroeconomics, neuromarketing, working both at the academic level and doing marketing research projects for real companies that are actually reaching customers and so on. But he was telling me that the question is, what is the kind of, when one is going to make a decision about something, something happens in one's brain, and that might be detectable by, he's used fMRI and EEG and so on. Some of those things might be detectable a second or two before the decision is made for some kinds of things. But for other kinds of things, there's a kind of a picture that one has in one's brain somehow about some particular brand or product or objective or whatever. And Ming has sort of been interested in this question of how does one think about representing what that picture is? We might be able to detect particular neuron firings, and we might be able to have sort of a language level, a human language level way to say what we think about something. But there's the question of what is the profile of that when it's actually in the brain, so to speak. And that's something that has been an objective to understand. So our next award here goes to Ming Shu from UC Berkeley. And oh, look at all these interesting. Okay, so this is I think everybody's brain is laid out a bit differently. So whoever's this is, these are, I guess, the areas that light up in connection with different kinds of attributes and which can be associated with different brands and so on. All right, well, our next award goes to Carol Johnstone from Fermilab. Carol has been involved in many kinds of accelerator projects at Fermilab, and generally in, you want a particle beam of this kind delivered to this place, Carol is the person who gets to figure out how to make that happen. She got her PhD nuclear physics, studying pion scattering and at Los Alamos, and then started working with Wolfram language and developing Mathematica notebooks to create advanced fixed field alternating gradient accelerators, and to essentially solve the equations associated with geometric orbit calculations for those kinds of accelerators. And the goal is to make the machine operate in a stable way and deliver the beam that one wants to get delivered. I think a significant fraction of all of Fermilab's beam deliveries have worked through Carol's system and built in Wolfram language. Now, I think she's worked on a whole variety of experiments, including the muon G-2 experiment that has had some notoriety recently in some of its results. Also on an experiment to look at muon electron conversions that violate muon number. That's another Fermilab experiment. Her most recent work has been on other kinds of beam production for things like scanning cargo, essentially doing using particle beams to detect things like heavy elements and so on, and then also using it for cancer therapy. And I think there are two different techniques, as I understand it, that Carol has been involved in. One is heavy ion acceleration, to be able to use heavy ions. She was just describing to me a new technique called flash therapy, in which one is delivering a high intensity of radiation for a very short time. And that's this high intensity with the appropriate ions being delivered, one can destroy the DNA of tumors, but not other tissue. And being able to figure out how to do those quick bursts of beam delivery is apparently a non-trivial problem, because the two different technologies of cyclotrons and synchrotrons that have been traditionally used for particle acceleration, somehow one has to go somewhere between those to achieve what needs to be achieved. And she's also worked on the creation of heavy isotopes, of radioactive isotopes to be used for radiation therapy. Her work is particularly significant for the new National Center for Particle Beam Therapy in Waco, Texas, that's under construction right now. So our award here goes to Carol Johnstone of Fermilab. All right, our next award of the evening goes to Jiang Hoon Lee, who is a mathematics teacher at Paju Girls High School in Paju, South Korea. And Jiang Hoon has really been a great pillar of the Korean Mathematica and Wolfram language community. Just done a huge number of things with our technology ever since he started using it in 1994 as part of his project in school in mathematics. He says he spends at least 2 hours a day using Mathematica and Wolfram language, and yeah, I'm sure I average at least that as well. So it's and I suspect many of our Innovator Award winners are in the same category, and it's just I'm glad everybody enjoys it. So Jiang Hoon has been using Wolfram language and Mathematica in his own teaching for many years, but he's also developed an online textbook called Mathematica Lab, and he also has his maththought.com website, which has had a couple of million visitors, and he's also creates content for Nava.com, which is the main Korean search engine, etc. website, where he has many other viewers and visitors. He's been recognized by the Korean Ministry of Education with the Korea Mathematics Education Award and the Science Teacher of the Year Award in Korea. And well, we're very happy to give him our Innovator Award this year. And I think there are some examples of some 3D printing artifacts created by his students. And I had the pleasure of meeting Jiang Hoon and some of his students in 2014 when I visited Korea for the International Congress of Mathematicians there. And it was it's great to see the kind of interesting and creative uses of both Mathematica and mathematics that Jiang Hoon has managed to come up with. So thank you. All right, our next award this evening goes to Scott Martin, who is at Harvard University and usually is right in my neck of the woods in the Boston area, but apparently today is in Manaus, in Brazil, in the center of the Amazon jungle. And there's a reason for that, which is that his research involves doing things with the Amazon rainforest. He studies molecules and their production by plants, and how and what kinds of volatile organic compounds plants can produce. And he's been using Wolfram language for a very long time, and got his PhD in chemistry at Caltech, and has been working in atmospheric and chemistry since then. I think he's also been involved with some software technology, for example, HDF, and he created an HDF5 package for Wolfram language. He's interested in all sorts of environmental challenges to do with air and water pollution and so on. I noticed from the notes here that he first started using Mathematica when it was at version 2.2 in 1993. And most recently, he was telling me that he's been studying how plants in the Amazon jungle produce a variety of kinds of volatile organic molecules, and how this complicated cycle that exists in the way that those molecules affect the seeding of clouds to produce rain, which then affect the plants that then produce more of these molecules and so on. And apparently the thing that has been, what's taken him to Brazil at this time is a new experimental technique, which is the ability to actually sample the air above in the rainforest using drones. Apparently there are different problems in using drones in the Amazon rainforest than there are in the US. The regulations are different, but some of the places that you might want to use your drone are infested by river pirates and things like this. So that's a challenge. But I'm actually quite curious, because I've become interested in recent times in questions of chemistry, and Scott was describing to me some of the ways in which different sort of sizes of molecules get produced in different ways by biological organisms. And I'm really curious to understand that, because in a sense, biology is our only example of molecular scale computation, and hearing about this different sort of hierarchy of different kinds of molecules that can be produced is very interesting. So in any case, our next award here goes to Scott Martin. Next award goes to David Park. And David has been using Wolfram language for a very long time. I'm not quite sure what the first version that he used is, but I've seen his name forever and ever in what used to be Math Group, and more recently in places like Wolfram Community, but in particular in the production of a whole collection of very elegant code and packages for a whole variety of purposes, for doing various kinds of visualizations, for units, for tensor calculus, and so on. And for a while there, I think David was able to distribute these packages through a variety of commercial outlets. And we're hoping we'll be able to provide such outlets again real soon through our things based on our Packlet repository and so on. He's been involved in a variety of technology activities, working on cesium beam tubes used in atomic clocks and satellites, and so on. Oh, I see from my notes here, he's been using Wolfram language since Mathematica version 2. He's also a particular enthusiast of Grassmann algebra and Grassmann calculus. This is sort of it's in the general area of geometric algebra, which is kind of an alternative packaging of things like tensors, things like exterior calculus. Grassmann algebra, geometric algebra is sort of a different packaging of those things that all revolves around Clifford algebras and so on. And it's sort of interesting because I think for some reason, 2021 seems to be the year of geometric algebra, because I had heard comparatively little about it for a long time, even though John Brown, a late long-time Wolfram language user, had written books about it and so on. I wasn't hearing much about this whole field, although it was originally developed by Grassmann in the 1870s or so, at least was initiated at that time. But somehow this year, I have had 5 separate groups have been telling me that geometric algebra is the way of the future and the way to think about kinds of problems in physics and so on. And one of the things we're hoping to be able to do is to bring some of those groups together. But David Park is a sort of anchor member of that effort, with creating this Grassmann calculus application, and look forward to seeing where that progresses. So, and these are David Wright's very elegant demonstrations and code, and they're always a pleasure to see. All right, our next award goes to Edmond Robinson, who is based in Bermuda and is a visible member of the mathematical Wolfram language stack exchange community and the Wolfram community, has contributed much to that. He's originally from Bermuda. I think he was went to school in New Zealand for a bit, but he's as it says there, industrial mathematician. Seems like it's the description. And I know he's been involved in a series of different industries, from just regular finance, risk management, regulator, government regulation of finance, reinsurance, and now he's involved in an AI as a service business that focuses on optimization of call centers and so on. He's contributed to the function repository and has presented his work at several technology conferences. He has made use of Wolfram language in many applications. For example, using CDF at the Bermuda Monetary Authority to present results and so on. Now I suspect he's in the process of rather revolutionizing the company that he has recently joined, and allowing them to make use of the technology that we have in Wolfram language, and that Edmond is very expert in using to do data science, do visualization, optimize the things that they're working on. So our next award goes to Edmond Robinson. Our next award goes to Leonardo Ronchetti, who is based in Brazil, and he works on his project director for TechCon Engineering, which I think he's also the co-owner of TechCon Engineering and Consulting, company specializing in industrial construction design, particularly for offshore infrastructure. And Leonardo has been using our technology for a long time. I notice in my notes here that he has a PhD in offshore structures, which is an unusual, at least in this part of the world, perhaps is an unusual PhD topic. That's great. But one of his achievements was creating the analysis and decision-making software for lifting operations for offshore platforms, for cranes and such like. He was telling me he's been working a lot on crack analysis for concrete and steel structures, particularly in the maritime environment. And I kind of had the idea that if you have a dam made of concrete or something, that the dam has no cracks in it. But Leonardo was telling me it's never no cracks. There are always some cracks. The only question is, are there cracks that are critically important cracks, or are there cracks that you don't have to worry about? And he's been developing the technology using Wolfram language to use machine learning and other things to analyze that, and to be able to go and use some autonomous vehicles to go and study underwater structures and go and analyze the images from them, find cracks, try to understand whether these cracks are critical or not. So, and this is particularly relevant apparently when you are dealing with structures that are made of concrete or steel or where, for example, a ship ran into them at one time. And it's like, how badly were they damaged as a result of that? That's what Leonardo's company, that's the kind of thing they are involved in analyzing. So our next award here goes to Leonardo Ronchetti. And those, I suspect, are pictures of his crane, I think also made using System Modeler. All right, our next award this evening goes to Fernando Sandoya. And Fernando is a professor at the ESPOL University in Ecuador, and also the founder and CEO of SolOp, a technical consulting company. And he's used technology for a long time, teaching at the university, mathematics, operations research, numerical analysis, and so on. He has used our technology as the primary tool in those courses. He's also had in his business, he's used our technology to do many kinds of products for many different purposes. He was telling me earlier that he's recently developed a kind of a computational contract application of Wolfram language for the Ecuadorian government for environmental, for permitting for environmental purposes, where there was previously a long and fraught with difficulties human chain of approval necessary for these environmental permits. And Fernando has developed a Wolfram language application that uses machine learning and other techniques to be able to automatically kind of grade these applications for environmental permits, an interesting use of kind of the computational contract kind of idea. He's done work for a whole variety of companies, for the largest food manufacturer in Ecuador, for doing reverse logistics for used tires in Ecuador, and dealing with predictive analytics for transportation of containers for ports in Ecuador, and also been involved in other kinds of activities around machine learning and the application of our technology in business intelligence and so on. He's also a Wolfram U instructor. Yes, and another thing I noticed here in the notes is developing Wolfram language application using machine learning for a large credit bureau in Ecuador. So our next award goes to Fernando Sandoya. And all right, our next award goes to Enrique Bilches Quesada, who is at the National University of Costa Rica. And he has used Wolfram language for more than 20 years, and teaching courses in mathematics, operations research, and programming. Started using Mathematica 25 years ago as a college student, and has developed a whole variety of packages for teaching linear algebra, differential integral calculus, finite mathematics, and has written a variety of books in this area, as well as packages for doing these kinds of things. I'm noticing from my notes here also a package in for discrete structures written in one of the native languages of the Costa Rican area. That's interesting. That's something I have not seen, and I've not seen that done. I'd be interested to see how that works. Yes. So one of Enrique's books is Mathematics for Engineering through the Use of CDFs, which integrates a whole collection of CDF applications for many different kinds of purposes, for learning how to use mathematics in engineering, and that's another one of his achievements. We're pleased to present our next award to Enrique Vilches Casado. Our next awardee is James Wyant from University of Arizona. James has been using our Wolfram Language and Mathematica since 1989, and he's been involved in optical sciences forever. He's started two companies in that area, and using interferometry for testing properties of surfaces, and both of these companies he has successfully built up and sold. In between those two companies, he became the founding dean of the College of Optical Sciences at the University of Arizona. For people who don't know, the University of Arizona has a very distinguished optical sciences operation. It and Rochester are the two great optical sciences places in the US. Notably, James got his PhD at Rochester. James was telling me that there are now 100 faculty, 100 professors in the optical sciences school at University of Arizona, a huge concentration. James has used Wolfram Language and Mathematica to teach his courses on optical testing and interferometry. I know he has been responsible for stimulating some very interesting usage of our technology by other people and other companies in the optical area as well. And one of the things that brought him to my attention many years ago is he was one of the very early users of Web Mathematica, and he put online a thing for computing Zernike polynomials, which at the time I'm embarrassed to say now, had never heard of. And that was my first introduction to Zernike polynomials. I subsequently learnt much more about them, and even at one time was wondering if I really wanted to absolutely optimize my vision and my glasses and so on, which level of Zernike polynomials should I be using to create the lenses that I need? And the answer is not much, but Zernike polynomials are something that is important for characterizing kind of distortion of optical distortion from astigmatism onto the higher order versions of that same kind of thing. And as I say, I at least got introduced to them through Jim's Web Mathematica, early Web Mathematica system, which is still running, along with several other examples that he put online and has been able to provide to the world to use in optics classes and other kinds of things. Jim is now, he says, officially retired, although I think he's one of those kinds of people who doesn't really quite retire. And he was telling me that during the pandemic, his retirement activity has been returning to his early interest in ham radio, but instead of talking to people now, he's been talking to the moon, and in particular, using ham radio frequencies to bounce signals off the moon to detect them back on Earth, and has been working with a group that has been interested in that. Our next award here goes, let's see what pictures we have. Oh yeah. Oh, look at that. There's some Zernike polynomials. I don't think that's the most interesting Zernike polynomial. We should have picked a higher Zernike polynomial. But there's an example. Well, anyway, it's a great pleasure to present our next award to James Wyant. All right, moving on. Our next award goes to a company General Vibration Corporation. It's been a long time user of our technology. General Vibration is concerned with making haptic devices, from the joystick that vibrates when you touch it, to other kinds of touch-based feedback devices. And in particular, the challenge is, how does one take low-cost actuators and make them provide a kind of a pleasant experience? I gather that the 1 or 2 hertz vibration is what us humans like, and the things you get from spinning weights and so on tend to be more in the 100 hertz range, which isn't what us humans like. So it's a challenge to kind of down convert those vibrations. And General Vibration has been involved in creating these kinds of devices using our technology. They've been using John Houston, who was the founder and president of General Vibration, was first exposed to Mathematica around 1993, and they've been using it since that time to do things. And I believe they've worked with recently with our technical services team on some new developments. Just a couple of years ago, Sony's interactive entertainment division licensed their whole haptics intellectual property portfolio, including their game controller mechanisms. And so they continue to work on how do you make things feel right, so to speak, in using devices. And to accept the award on behalf of General Vibration, we have here Rob Morris, who I happen to know because he's a former summer school and former employee of our company, actually, from long, long ago. And more recently, educator who's worked in his other life, worked with our technology, but has been for a long time working with General Vibration. So like to present this to General Vibration Corporation. Our next award goes to the Houston Methodist Research Institute. This is where they've been using Wolfram language and Mathematica. This is Vittorio Cristini, Bill Wang, and Joseph Butner. Joseph is here to accept this award. They've been using Wolfram language to do a whole variety of modeling related to medical processes, sort of the physics and mathematics of biomedicine, particularly in the area of oncology, microfluidics, and so on. And the goal is to optimize treatment, particularly on the oncology area, and to figure out, both at a microscopic level and at a more macroscopic level, how to optimize the things that should be delivered. And I was learning at lunch about lots of interesting things about immunotherapy, and well, of course, there are. I was asking about the new opportunities that RNA, sort of made-to-order RNAs embedded in lipid nanoparticles and so on could provide. And Joseph was explaining some of the challenges associated with delivering these things to the right places in the body, and particularly some sort of new discoveries about the kinds of ways that even the coatings of blood vessels have kind of zip code information that sort of says what tissues are behind them as a way to deliver payloads to the right place. But in any case, I gather that mathematical and Wolfram language have been widely used by the group at Houston Methodist to work particularly on things like checkpoint inhibitor immunotherapy. So our next award goes to Houston Methodist Research Institute. Our next award goes to the Virginia Tech Math Emporium, and that will be accepted by Jessica Schmally. The Math Emporium was founded more than 20 years ago and has been a mathematical and Wolfram language-based operation from the very beginning. And it's a way of delivering, it's kind of a pioneering way of delivering math course content, particularly to first-year college math students. Apparently, it's at Virginia Tech, it's a physical, it has been in pre-pandemic and post-pandemic days, a physical assembly of a large number of computers in one place. And it's had 8,000 students going through, being served by the Math Emporium each semester with a variety of courses. The courses have been presented using Wolfram language, and the quizzes developed using Wolfram language with lots of variations for each question and so on. And the results are stored in XML files created by Wolfram language for their testing system. The original testing system was created by Lawrence Sewell, who passed away a couple of years ago now, it's but the Virginia Tech Math Emporium has ended up being a model that for providing math education that has been followed now at a variety of other schools, and it's been a very successful model that has both saved a lot in textbook costs and also provided sort of supported self-paced education that's a mixture of computer education and help from humans organized in this way. And it's so it's an interesting model, which I know we've been involved with several other schools that have made use of the Virginia Tech Math Emporium model, and it's very nice to see that. So our final award of the evening goes to the Virginia Tech Math Emporium. All right, well, thank you all very much. This is, I think, let's see, for those who we didn't manage to get on camera before, yeah, let's all hold up these awards. That's a good scheme.
Thank you all so very much, and I hope you can hear the thunderous applause from everybody at home in all the corners of their world.
Thank you very much, and congratulations to everybody. And we really appreciate all the fascinating ways in which you make use of the things that we put so much effort into. And it's really wonderful to see all of this.